Hi, in today's tutorial we'll be looking at a recursive sequence problem from the Further Mathematics paper 2 of June 2022. The question says a sequence un is defined recursively by u0 equals half un plus 1 equals e to the un all over un plus 2. Given that a function f is such that the interval 0 to 1 is mapped onto the set of real numbers, is defined by f of x equals e to the x all over x plus 2. Roman 1. Find f prime of x and f prime prime of x. Roman 2. Obtain the table of variation of f. 3. Use mathematical induction to prove that for all n belonging to the set of natural numbers, 0 is less than or equal to un less than or equal to 1. Show that for all x belonging to the interval 0 to 1, the absolute value of f prime of x is less than or equal to 2/3. 5. The equation f of x equals x has a unique solution. 6. For all L belonging to the interval 0 to 1, the absolute value of un plus 1 minus L is less than or equal to 2/3 the absolute value of un minus L for all n belonging to the set of natural numbers, and that in general the absolute value of un minus L is less than or equal to half into 2/3 to the power n. 7. Hence, show that the sequence un is convergent. Okay, we begin with the first part of the equation. F of x equals e to the x all over x plus 2, and we are required to find f prime of x and f prime prime of x in that first part. F of x being a quotient, we then have to use the quotient rule to differentiate, and we start by multiplying the denominator by the differential of the numerator. So we get x plus 2 times e to the x, which is the differential of e to the x, minus the numerator times the differential of the denominator. X plus 2 differentiated gives 1, all that over the square of the denominator. So we get x plus 2 all squared at the denominator. Factorizing e to the x at the numerator, we get x plus 1 times e to the x all over x plus 2 all squared. So the simplified form of f prime of x is x plus 1 into e to the x all over x plus 2 all squared. To have the second derivative, we have to differentiate the first derivative, and it is still a quotient, so we have to use again the quotient rule. We start by multiplying the denominator by the differential of the numerator being a product. We have to use the product rule to differentiate it. So x plus 1 times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of x plus 1, which is 1, minus the numerator times the differential of the denominator. To differentiate the denominator, we have to use the power rule, which would then give us the derivative as 2 into x plus 2 times the derivative of the bracket x plus 2, which is 1, all over the square of the denominator. So x plus 2 squared all squared, which gives x plus 2 to the power 4. And in order to simplify, we notice that x plus 2 times e to the x is common at the numerator, so we factorize it so that we get x plus 2 times e to the x into x plus 2 into x plus 1 plus x plus 2 minus 2 into x plus 1 all over x plus 2 raised to the power 4. And upon simplification, we then have that f prime prime of x is equal to x squared plus 2x plus 2 into e to the x all over x plus 2 raised to the power 3. In the second part of the question, we are asked to draw the table of variation of f. In order to draw the table of variation of f, then we have to make use of the derivative of f, which is f prime of x equals x plus 1 into e to the x all over x plus 2 all squared. And before we proceed, the table of variation is always important because it ends up revealing to us the monotonicity of the function, and the monotonicity of f is very crucial in this question. The first thing we notice is that for all x belonging to the interval 0 to 1, x plus 1 is greater than 0, x plus 2 greater than 0, and of course e to the x is always greater than 0. From the analysis, we can then see that f prime of x is clearly greater than 0 in the interval 0 to 1, which implies that f of x is increasing in that interval. To draw the table of variation, we also need the images of the boundary values of the domain of f of x, which are f of 0 being half and f of 1 being e over 3 when you substitute 0 and 1 in the function f of x equals e to the x all over x plus 2. And so we can now present the table of variation, which clearly shows that in the interval 0 to 1, f prime of x is positive, and so f of x is increasing in that interval from the image of 0, which is half, to the image of 1, which is e over 3. In the next part of the question, we are asked to prove that for all n belonging to the set of natural numbers, 0 is less than or equal to un less than or equal to 1 using mathematical induction. So we start by noting that u0 is half and un plus 1 equals e to the un all over un plus 2, which clearly shows that un plus 1 is f of un. Now, u0 equals half, and clearly half belongs to the interval 0 to 1. So we can conclude that the statement 0 less than or equal to u0 less than or equal to 1 is true. Now suppose 0 less than equal uk less than equal 1 is true, then we can have that f of 0 is less than or equal to f of uk less than or equal to f of 1. And we can only move from the statement assumed to this other statement because of the fact that f is increasing on the interval 0 to 1. If f of x were not increasing in that interval, we cannot move from this statement that we have supposed to be true to this other one, which is crucial for us to do the proof. Proceeding, then we would have that f of 0, which is half, is less than or equal to uk plus 1, because f of uk is equal to uk plus 1, following the fact that un plus 1 is equal to f of un, and that is less than or equal to e over 3, so that 0 is clearly less than or equal to uk plus 1 less than or equal to 1, since the interval half to e over 3 belongs to the interval 0 to 1. We can then conclude that for all n belonging to the set of natural numbers, 0 is less than or equal to un less than or equal to 1 by mathematical induction. In the fourth part of the question, we are asked to show that for all x belonging to the interval 0 to 1, the absolute value of f prime of x is less than or equal to 2 over 3. So to do this proof again, we have to rely on the monotonicity of f prime of x this time. We start by looking at the derivative of f prime of x in order to arrive that monotonicity. F prime of x differentiated would give f prime prime of x, which we obtained in the first part of the equation as x squared plus 2x plus 2 times e to the x all over x plus 2 raised to the power 3. And clearly all the parts, both the numerator and the denominator, will all be positive in the interval 0 to 1, and so f prime of x is always greater than 0, implying that f prime of x is strictly increasing in the interval 0 to 1. f prime of x being x plus 1 all over x plus 2 all squared times e to the x, we need to find f prime of 0 and f prime of 1 to proceed. So when you substitute 0 in f prime of x, you get f prime of 0 as 1 over 4, and f prime of 1 would lead to 2e over 9. So f prime of x increasing on the interval 0 to 1, 0 is less than or equal to x less than or equal to 1. Following that, f prime of 0 is less than or equal to f prime of x less than or equal to f prime of 1. So proceeding, then we would have that 1/4 is less than or equal to f prime of x less than or equal to 2e over 9. Remember, we are seeking to prove that the absolute value of f prime of x is less than or equal to 2 over 3. So we'll rely on this second part of our inequality to arrive at proof, so that we can then write that f prime of x is less than or equal to 2e over 9. And since we want to show that the right hand side of that inequality should be 2 over 3, we compare 2e over 9 with 2 over 3, and to better do that comparison, we make their denominators the same. So we write 2 over 3 as 6 over 9. Clearly, e being approximately 2.72, 2 times 2.72 would be less than 6, so that 2e over 9 is less than or equal to 6 over 9, and 6 over 9 being equivalent to 2 over 3. It means that if f prime of x is less than a number that is less than 2 over 3, hence we can conclude that the absolute value of f prime of x is less than or equal to 2 over 3 as specified in the equation. In the fifth part of the question, we are asked to show that the equation f of x equals x has a unique solution. In order to verify that the equation f of x equals x has a unique solution, we need to verify two things. The first one is that we will need to verify that the function f of x equals x is either strictly increasing in the interval 0 to 1 or strictly decreasing. And the next thing will be that the function f of x equals x or f of x minus x equals 0 crosses the x-axis in that interval 0 to 1 at least once. To begin, we start by looking at the function in a way that we can clearly work with it without difficulties. So f of x equals x can be written as f of x minus x equals 0, and we can further redefine that function as h of x equals f of x minus x. Since we need the monotonicity of the function in that interval, we can then differentiate both sides of that statement in order to have the derivative of the function as h prime of x equals f prime of x minus 1. And from previous work, we had that the absolute value of f prime of x was less than or equal to 2/3. So the value of f of x, or the absolute value of f prime of x, would always be less than 1 in that interval, which implies that f prime of x minus 1 then will always be negative. So we can conclude that h prime of x will always be less than 0. The conclusion then from this analysis is that h of x is strictly decreasing for all x in the interval 0 to 1, since its derivative is always less than 0. Further, we need to verify whether the function h of x crosses the x-axis at least once. For it to do so, we would rely on the intermediate value theorem, in which we have to look whether h of 0 and h of 1 have opposite signs. So we start by verifying h of 0, which is f of 0 minus 0, and this gives half, and clearly half is greater than 0 or positive. H of 1 equals f of 1 minus 1, and f of 1 being e over 3. E being 2.7 and is less than 3, it means that e over 3 is less than 1, and so e over 3 minus 1 is less than 0. So we can clearly see that h of 0 and h of 1 have opposite signs. So the conclusion we can make from the analysis then is that h of x crosses the x-axis in the interval 0 to 1 according to the intermediate value theorem. So finally, we can then make a general conclusion that since h of x is strictly decreasing on the interval 0 to 1 and h of 0 and h of 1 had opposite signs, then h of x equals f of x minus x equals 0 or f of x equals x has a unique solution in the interval 0 to 1. In the sixth part of the question, we are asked to prove that for L belonging to the interval 0 to 1, the absolute value of un plus 1 minus L is less than or equal to 2/3 the absolute value of un minus L for all n belonging to the set of natural numbers. Now, to do this proof, we have to rely on the previous part where we established that the absolute value of f prime of x is less than or equal to 2/3, as well as applying the mean value theorem on the left hand side of that relationship. So proceeding with that application of the mean value theorem on the left hand side, we will then have that the absolute value of f of un minus f of L all over un minus L should be less than or equal to 2/3, where L belonging to the interval 0 to 1 is the unique solution of f of x equals x, which means f of L should be equal to L. Remember that f of un is equal to un plus 1, as we already saw in the previous part of the questions. So we can proceed to replace f of un by un plus 1, as well as replacing f of L by L according to the fact that f of L is equal to L, which is the unique solution of the equation f of x equals x. So cross multiplying this inequality will then have that the absolute value of un plus 1 minus L is less than or equal to 2/3 the absolute value of un minus L for all n belonging to the set of natural numbers. We are also required in this part to prove that in general the absolute value of un minus L is less than or equal to half into 2/3 to the power n. This proof, to do it directly, may not be easy, so we rely again on an indirect method, namely proof by mathematical induction. To begin, we let p of n to be that statement and then seek to prove that p of 0 is true. To do that, we start by noting that L belongs to the interval 0 to 1, so L should be greater than or equal to 0. Multiplying both sides by -1, we have that negative L is less than or equal to 0. Then, since we would be seeking to have the relationship u naught minus L and u naught being half, we can then add half on both sides of this inequality so that we get half minus L less than or equal to half. And clearly we can then see that u naught minus L is less than or equal to half. So verifying now with the original statement that we are seeking to prove, we can see that the absolute value of u naught minus L is less than or equal to half. And when you substitute n equals 0 in the right hand side of that inequality we are seeking to prove, you would clearly see that it is half, because half into 2/3 raised to the power 0 is half, and so p naught is true. We now suppose that pk is true, so that we get absolute value of uk minus L being less than or equal to half into 2/3 to the power k, and then we proceed to use that and prove that the statement pk plus 1 would also be true. We start by multiplying both sides of that assumed statement by 2/3, so that we get 2/3 into the absolute value of uk minus L less than or equal to 2/3 into half into 2/3 to the power k. And in the previous part, we had also established this other first part of our inequality that I've written, in which the absolute value of uk plus 1 minus L is less than or equal to 2 over 3, the absolute value of uk minus L. We had established this in the previous part using the mean value theorem. This other statement is obtained by simplifying the right hand side of the previous statement that we modified in our assumption step. So the conclusion we have to make is that if this statement is less than or equal to the right hand side and the left hand side is less than or equal to that statement, then the left hand side would be less than or equal to the right hand side, according to the transitivity of the less than or equal relation. And so the conclusion we can make then is that the absolute value of uk plus 1 minus L is less than or equal to half into 2 over 3 to the power k plus 1, so that p of k plus 1 is then true. So we can now conclude that the absolute value of un minus L is less than or equal to half into 2 over 3 to the power n for all n belonging to the set of natural numbers by mathematical induction. In the last part of the question, we are asked to show that the sequence un is convergent. To do that, we have to start by noting that the absolute value of a function is always greater than or equal to 0. So we can then write that the absolute value of un minus L is bounded to the left by 0, so that we can then conclude that 0 is less than or equal to the absolute value of un minus L less than or equal to half into 2 over 3 to the power n. In a situation where un is defined recursively, in order to establish its convergence, we mostly have to find the limit of un. This relationship tells us that we can get the limit of un if we apply the sandwich or the squeeze theorem. So in order to do that, we would simply find the limit of all the parts of this inequality, compare them, and then see how to arrive the limit of un. So taking the limits of all the parts of the inequality there, we would have that the limit as n tends to infinity of 0 is equal to the limit as n tends to infinity of half into 2 over 3 raised to the power n. Notice that half into 2 over 3 to the power n is a geometric sequence with common ratio being 2 over 3, the absolute value of 2 over 3 being less than 1. It means that that geometric series converges, and so the limit of that statement is 0. Since the limit of 0 is 0 and the limit of the statement on the far right is also 0, we can conclude that the limit as n tends to infinity of the absolute value of un minus L is equal to 0 according to the squeeze or the sandwich theorem. We can then proceed to have that the limit as n tends to infinity of un would be L, and we had already established that L was the unique solution of the equation f of x equals x in the previous parts of the equation. L being unique means the limit as n tends to infinity of un is unique, and once the limit of un is unique, it means that un is convergent. Thanks for watching, and if you are new to this channel, please consider subscribing and also activating the notification bell so that anytime I post a video, you would get it handy.